All right, we're going to finish up chapter 6. This is the last section in here that we'll cover. And what we're going to do is we're going to use all of our factoring techniques to solve. All right, so we're going to be looking at quadratics, what quadratics are, and how we can find the solutions to quadratics through factoring and through graphs. All right. So first of all, let's talk about what a quadratic is. We're going to look at cubics too, but that's farther down in the homework there. Okay, so a quadratic. Basically, it's in this form. All right. We have an x squared, x, no x, kind of a pattern. They can also look like, the b can be 0 and we can have a c, or vice versa. The c can be 0 and we can have a b. So they can look in different ways, but basically what you're looking for is that the highest power on your x term is the 2. Okay, so this is different than linear. Remember, linear, the highest power on your x term was 1, and therefore it made a line. Well, these all make parabolas. So these are parabolic shapes. Parabola. All right? And we're going to look at parabolas more in depth later. But basically that's what it is. What we want to do is, let's just say we have this parabola right here. Okay? What we want to do is we want to see, where does the parabola equal 0? What kind of an x do I need to put in here so that my y term is equal to 0? This is also equal to f of x, which is my y. So y is equal to 0. Well, on my parabola, where is y equal to 0? Well, isn't it equal to 0 right here and right here, right? If I have to choose two places, okay, I've got an x-coordinate of, let's just say, 2, but my y-coordinate is 0, and maybe this is 4, 0, okay? So my solutions are my x-intercepts, right? The solution to this is the same as my x-intercept graphically. All right, so my solutions are my x-intercepts. Okay, and these are also called the zeros of a function. It's where y is equal to 0. Okay, so what I'm going to do is I'm going to look for the solution here, okay, and then graphically I'm going to check to make sure that those are the intercepts, the x-intercepts. All right, so we need all that information. And then when we get to cubics, I'll cover that then. And then we need to know also a peculiar property about multiplication in 0. If I have two things multiplied, a times b, and they equal 0, then one of two things has to be true. Either a has to be 0, or b has to be 0. And there's no other way that I can take two things and multiply them together and get a 0 for an answer if one or the other, or both, aren't 0, right? I mean, there's just no way. I can't have two numbers multiplied and come to 0 without one of them being 0, which is very useful. This is a very useful statement right here. All right? So let's take a look at what we have up there. We have t plus 3, t minus 12 is equal to 0. Do I have this situation right here? Do I have two things multiplied is equal to 0? I think I do. I have this as a product times this. So it's the product of t plus 3 times t minus 12, and that has to equal 0. Well, since I do have this stipulation right here, now I can say either this has to be 0, or this has to be equal to 0. One of the two has to happen, or both. Okay, so now I'm looking for the solutions by using this. This is called the principle of zero product principle. I don't know how they word it in here. Zero product principle, I think. Well, it'll say in the next one, I think. So now I've turned my quadratic into two separate linear equations, which can be solved quite easily. I can subtract my 3 across, so t is equal to -3, and I can add my 12 across. Add 12 across. So I have t is equal to 12. All right, there's my two solutions. Now, why do I get two solutions? Because most parabolas cross twice. There's one solution and there's another solution. All right, this tells me how many answers I'm going to get at most. I can get up to 2. Now, my quadratic can also just touch in one spot, and that's called a double root. Okay, we'll see one of those. All right, and another situation can be where it's hanging in the air and never crosses. All right, we're going to get to these later, in not this chapter, but in further chapters, and then we've got our imaginary numbers in here. So these do have solutions as well. They're just not in the real number system. They're in the complex number system. So for right now, we can either have it crossing twice, so we're going to always look for our two solutions, or it can touch once, and it's got that double root, double solution, but it's the same number, so we only list it once. Okay, so let's try it. If I put a -3 in for t here, I get -3 plus 3, which gives me 0. I get a -15 on this side, but 0 times -15 is 0. That one works. Or if I put my 12 in here and here, then I have 12 plus 3 is 15. But 12 minus 12 is 0, and 15 times 0 is 0. So either one of these two will work. So when I put these in, make sure that you use a comma to separate your numbers, but don't put spaces in. Okay? I don't think it likes spaces. If you put a space in between here, it'll kick it out. All right? Zero factor property. That's what I was trying to say. All right. Do we have two things multiplied and are they set equal to 0? Yes, I have one thing here times this thing there. It's equal to 0. So therefore I can use my zero factor property. So either 4s has to be equal to 0, or 13s plus 9 has to equal 0. One or the other has to be true, so I can put an either or in there. And I can solve these separately. I'm solving for s, so I'm going to divide 3 by 4, both sides. 0 divided by 4 is 0. On this one, I'm going to solve for s by first subtracting my 9 across. My 9's are gone. 0 minus 9 is -9, and then I would divide through by 13 both sides. So s is equal to -9/13, or 0. Okay, the 0 wipes out this term, turns that piece of it into a 0. 0 times whatever is 0. And the -9/13 put in here and here wipes this term out to a 0, and then this becomes whatever, but it doesn't matter again because you're multiplying by 0. So you would put those in as two separate answers with a comma between them. All right? Okay, so now we've been given something like this. Okay? Do I have two things multiplied that equal 0? No, I don't. I have addition. And I have no rules about addition. I don't have a solid rule that says if I add these two types of numbers, then this has to happen. There's just no rule like that. So instead, what we're going to do is we're going to turn our addition into multiplication so we can use our rule. And the way that we turn addition into multiplication is to factor. All right? So we're going to factor first. We're going to find the solutions by factoring, then we're going to set each piece equal to 0. And then on this one, we're going to actually start checking the calculator. I want to start bringing that graphical piece into it. All right? So the first thing that you need to do is you need to analyze what kind of factoring problem you've got here. Well, I look at it and I say, well, 3 terms. That rules out difference of squares, sum of cubes, difference of cubes, factor by grouping. All those are gone. GCF, do I have a GCF in here? No, there's nothing in common between these. So I look at this and I go, okay, that's probably one of those easy trinomials, right? It's in the x squared, x, no x pattern. So I'm going to try factoring using that method. So I know that this broke down into 2 binomials that were multiplied. I know my variable is a v. I look at my back piece here, and it's a plus, so they both have to be the same, and they both have to be positive. And so now I'm going to make factors of 40, and I know I have to add to 13, right? So I've got 1 times 40, I've got 2 times 20, I've got 4 times 10, I have 5 times 8, and as soon as I hit it, I can stop. Okay, these add to 13. There's only going to be one pair that do. So I've got 5 and a 13 here, 5 and an 8 here. Okay, at this point I could re-FOIL to see if I've done this correctly, but now I do have one piece times another piece and it's equal to 0, so it qualifies now. So now I can say either v plus 5 is equal to 0, or v plus 8, it has to be equal to 0. Either or. These are 2 easy linear equations which I can solve very easily by this one subtracting 5 across, isolating v. This one we're subtracting 8 across. Okay, this is gone, so we have v equals negative 8. Okay, we have to put an or in there. It can't be an and. V can't be 2 different numbers at the same time, right? Okay, so let's do a couple things here. First of all, let's check to see if this is correct by plugging these back into the original equation to see if they equal 0. Okay, that's our first step. All right, so I'm going to start with my negative 5. So I have a negative 5 squared plus 13 times negative 5 plus 40. And that's supposed to equal 0. Now I can just use my calculator here just to plug it all in just for time's sake. Plus 13 times negative 5 plus 40. Yep, it works. We're going to do it again with a negative 8. Negative 8 squared plus 13 times negative 8 plus 40 should equal 0 as well. So I'll try that one again. Okay, so in a testing situation, you want to really make sure that these are working. You should test it with some method. I'll show you another method here in just a second. Okay, that one works too. Okay, so I've got my 2 solutions, a negative 5 and a negative 8. Well, now remember our graphical piece of this. We have a quadratic that should be crossing at negative 5, 1, 2, 3, 4, 5, 6, 7, 8. Right here and here. 1, 2, 3, 4, 5. So the quadratic should look like this if we would graph it, if we've done it right. So let's go back into our y equals and let's put it in. Remember, this is our variable. I haven't done this in a while. X squared, v squared, who cares, right? Plus 13x plus 40. Let's graph it and see. Yeah, wow. Looks exactly like that. It looks like it's crossing at 1, 2, 3, 4, 5, 6, 7, and 8. But just to be sure, let's get into the table and make sure that those are indeed exactly zeros. See how y is equal to 0 there and there. So there's your verification that indeed we do have our two zeros. So you have really, you could factor or you can do it graphically, however you'd like. All right. Now here we have, I'm not going to do all of these, but here we have something that's not quite set up properly. So you want to get it set up so that everything is off to one side and your one side is 0. So we're going to add a 2v across, first of all. V squared plus 2v equals 24, right? And then we're going to subtract our 24 across. So we have v squared plus 2v minus 24 should give 0. Now we're going to proceed from there. Factor, 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 right? Factor, set each piece equal to 0 and solve each piece. Piece of cake. Same thing here. Oh, this is, no, okay. Let's look at this one. Boy, I've been writing large lately. I haven't been getting a whole lot out of my screen. It goes full pretty quickly here. I think I'm writing really large though. All right. All right, so we're going to factor. I've got my variable in the front. My signs are the same, and they're both negative. Factors of 25. You have to add to 10. So I'm going to put this in here. Okay? Then either c minus 5 is equal to 0 or c minus 5 is equal to 0. So either c is equal to 5 or c is equal to 5. That's one of those double root ones, so I wanted to show you that. So let's just get it in here and just see if it only crosses once, and if it does it cross at 5? Yep, it touches once right at 5. Doesn't cross over, but it just touches it. And let's go to, yep, there it is, 5 and 0. And there isn't another one in there. That's it. Okay, so you can see from the picture that it's crossing at 5, or touching at 5. And then the table verifies that. So this one you wouldn't want to put in 2 5s. You just want to put in just one answer. That's it, because you don't want to ever double them up. Okay, the other ones, when they have 2, when it crosses in 2 different spots, then you want to make sure you put both of them in. All right. All right, do I have something set equal to 0? No, I don't. So I'm going to subtract my 1 across. I still don't have products, I have subtraction, but I recognize this as a factoring problem. And I look at it and I say, okay, it's got the 2 terms. That means the trinomials are out. There's nothing common between them, so my GCFs are out. Can't be a difference or sum of cubes because I've got a square, but this is a difference of squares. This is a perfect square minus another perfect square. And what was that? That was 1 plus 1 minus. Square root of the front one goes in front, and the square root of the back one goes in the back. Now I have something times something is equal to 0, so I can say either this is 0 or this is 0. I've turned my quadratic into 2 separate linear, so w has to either equal -1 or w has to equal 1. So we can draw a really quick sketch of that very quickly because we know what it looks like. Okay? So here we would do 1 comma -1. And you can throw them in here. If I squared 1, I get 1. And if I squared -1, I get 1. So that does work. All right, let's try this one. Okay, so the first step is to get it set to 0. All right, so I'm going to subtract my 4c across both sides. I get my 0 on that side, so I have c squared minus 4c equals 0. There's my quadratic. Again, I don't have that last term. It's a 0. I look at this and I go, okay, it can't be the trinomial because it's missing that third term. It's not a difference of squares because this is not an even-powered variable. Can't be a sum or a difference of cubes because my highest power is a 2. So what about a GCF? Yep, I've got a GCF of a c in there, right? I'm going to divide through by c. C squared divided by c to the first is c. And minus 4, we've got our c's canceling, so this is our equation. Now I've got this times this equals 0. So either c is equal to 0 or c minus 4 is equal to 0. This one's already solved. This one says c is equal to 4. Okay, let's just check it on the calculator just because we can. Let's clear that out of there. We've got x squared minus 4x. Remember, we have to have, you can't put this in there. You've got to get this one in there. Okay? Should be crossing there and there. Yeah, that looks good. Verify it through the table. When x is 4, y is 0, that one looks good. And 0, 0. Perfect. All right. Okay, I have two things multiplied. But two things multiplied equaling a number other than 0, there is no hard and fast rule. So what do? Well, I have to get it set to 0. So I'm going to want to distribute this on this side. It's for an r squared minus 4r. And then I'm going to want to subtract my 45 across for an r squared minus 4r minus 45 equals 0. Now I'm going to analyze my factoring. I look at this and I think trinomial, easy trinomial. Break it apart, set it equal to 0, you've got your answers. Okay? I'll let you alone on that one. All right, so let's work on a couple cubics. Cubics, they all look like ax cubed plus bx squared plus cx plus d equals 0. Okay, they can have up to 4 terms like this. Well, they can have more too, but the highest power is a 3. So really what we're doing is we're looking for 3 separate answers. Remember on the quadratics, the highest power was 2, so we can have up to 2 answers. Now my highest power is 3, so I can have up to 3 answers. So the highest power on the variable drives the number of solutions. And again, my solutions are my x-intercepts. Okay, so my solutions to this equation here are my x-intercepts, which are my zeros. We use this in college algebra. We call them the zeros. They always talk about finding the zeros of the function. Okay, so really what you're doing is you're looking for the intercepts or the solutions. And for the most part, cubics look something like this. I mean, it depends on the numbers, how flat and how hilly this is, but it's going to cross up to 3 times. Okay? They can only cross twice, and they can cross once, but they have to cross at least once. Okay? So, again, we're going to be factoring. We need to use that rule about two things multiplied equal to 0. Here I have two things subtracted equals to 0, so I can't use it yet. So I take a look at what I've got here. Okay, I've got a factor. What do I have? I have a cubic, so I'm going to look for a sum or a difference of cubes. So remember, everything had to be a perfect cube. Well, 4 is not a perfect cube, so that just shoots that. I mean, every single piece would have to be perfect, and this one's not, so you don't look any further. Neither are these, by the way. So it can't be a difference of cubes. Can't be a trinomial because it's got the wrong power. Can't be a difference of squares if it's a cube. So I will say there's got to be a GCF in here that we can pull out. So between a 4 and a 36, we can pull out a 4. That's the highest number that goes into both of those evenly. And then we take the lowest power. So we're going to divide through by 4x and divide through by 4x. This gives me x squared, and this will give me minus 9. All right, now from before, we have to analyze whether or not we're finished. We've created this binomial back here that looks suspiciously like a difference of squares, so it can be factored further. So when you're doing your factoring, you have to factor completely. All right, so this 4x is just going to go along for the ride. And this can be broken apart into two separate binomials. 1 plus, 1 minus. Square root of the front one goes here. And the square root of the back one goes here. Now I look at each piece that I've created and I say these are all prime. I can't break them down further. So now I have something times something times something is equal to 0. Well, that means that one of these somethings has to be 0. So I do the same thing. Either this is 0 or this is 0 or this is 0. Now I've got my three solutions. I have three linear equations. I can solve each one individually. So x is equal to 0. Okay. I can subtract my 3 across. X equals negative 3. Or I can add my 3 across. X equals 3. There's my three solutions. Let's just check one. Let's just check this one in the original. 4 times 3 cubed minus 36 times 3 is equal to 0. Is that true? Well, it certainly better be. Otherwise, we've done something incorrect. 4 times 3 raised to the third power minus 36 times 3. Yep, it works. And so would the negative 3. And so would the 0. Now, the other way that we can check it is to graph it. Okay, so this is going to be some sort of a, let's use our graphing here, our graphing techniques that we know. We've got 0 here, we've got 3 there, we've negative 3 there, we've got 3 there. So this thing is going to look something like, oh shoot, I didn't hit it. This pen's harder to use than you think. It's gonna look something like that. So we're gonna put the original in there, 4x raised to the third power minus 36x. I'm going to graph. Yeah, see now, these are going way up high on this. Okay, so when it graphed, it went way up, it came back down, and then it went way back up again. So you can kind of see where they're crossing these three spots, and then we can use that table for verification to make sure. We've got 0, 0, we've got 3, 0, and we've got negative 3, 0. All right, but sometimes you can't see the whole picture as nice as this, because on ours, this thing was, this thing was shooting up like this, went off the page, and then went way down here and came back up. So it looks a lot steeper. than what I've got pictured here. But, okay, so the same thing here. You're going to factor the left side. You know, you've got a common t. And then you'll have a difference of squares left over, so that one should be good. Yikes. All right, what do we have here? Okay, I'll do these. I think both of these, 11 and 12, I think they're the same. So I'll do one of them for you. Let's just take a peek at 12. Yeah, they're the same. Okay, I'll just do one. 5x plus 7, 5x squared minus 11x plus 6 is equal to 0. Remember, I need that a times b equals 0 form. Do I have it? A times b is equal to 0. I do. Okay? This is like a, all of that, and all of this is like b. So I can say either 5x plus 7 is equal to 0, or 5x squared minus 11x plus 6 is equal to 0. Now if I was to multiply this out, my first term that I would get would be 25x cubed. That would be my highest power. Therefore, this thing is a cubic. So how many solutions am I looking for? Up to 3. I'm going to get 1 through here because it's linear, and I'm going to get 2 through this one because it's quadratic. Therefore, there's my 3 solutions. Okay? So this one's linear, and linear is really easy to solve in comparison to anything else. Okay, I'm going to subtract my 7 across and then divide through by 5. So there's one solution. X is equal to a negative 7/5. All right. What about this bad boy? Well, I look at it and I say, okay, it's got to be one of those trinomials. It's in that pattern, that x squared, x, no x. It's an AC method because my first coefficient is not a 1. So I've got to go through all that rigmarole of that AC method and the factor by grouping and blah, blah, blah. All right, so A is 5, C is 6, A times C is 30. I'm going to look at my signs. I'm going to be adding to my middle term of 11. All right, what makes A 30? What about 5 times 6? Do those add to 11? Yep, I'm done. All right, so I want to make it a negative 11. So therefore, I would do minus 5x minus 6x plus 6 equals 0. This right here is a negative 11x. Now I group. I'm going to group these front two. I see that these have a 5x in common. I'm going to divide each one by 5x. All that's left here is the x. This is a 1. It's actually negative 1. What's in common here? A 6. I'm going to pull out the positive 6 and see if they match. Do they match? Nope, I'm getting negative 1 here. So I'm going to switch this to a negative 6. Now what do I get? Positive 1. So just the x is left over. Remember, I'm trying to match this. And a 6 and a negative 6 divided is a negative 1. That's what I wanted. All right, so now I went from 3 terms to 4 terms to 2 terms. These two have the x minus 1 in common. X minus 1, and what's left over is the 5x minus 6. So on this one, I can say that either this or this is equal to 0. So I can say either x minus 1 is equal to 0, so x is equal to 1. So okay, so here's one solution. Here's another. Or I can say 5x minus 6 is equal to 0. And I can solve this one. So we have 5x is equal to 6. And then I would divide through by 5, divide through by 5. So x is equal to 6/5. There's your third. Now these you're not going to be able to see for sure on here. All right. So let's see what we can do here. And I'll tell you why you can't see them on here. That's why you need other methods. You can't rely on one method all the time. You can't say, well, I'm just going to graph them each and every time. Well, let me show you why you can't. Plus 6. Do that right? 5x plus 7, 5x squared minus 11x plus 6. All right. So it's coming up, it's circling back down around, and it's barely, I mean, it's really tight in through here. Okay? So I'm going to see if 1 is on my list. Yep, 1 is on my list. But you see I'm going by whole numbers here, and I've got fractions for my x's. And as a matter of fact, I've got fractions that are not ending anytime soon. I mean, look at 7/5. Let's go, just stop here. Look at 7/5. Is that one? Oh, that one, okay, that one does end. And what about 6/5? 6 divided by 5. 1.2. Okay, perfect. Then I'm going to show you something. The one in my example didn't end. It was irrational. And then you can't check them at all. So this one's 1.4. Okay, negative. And this one was 1.2. Okay, let me show you something. Oh, this is cool. All right, so I'm going back to my table set. Okay, my table set in here tells me how I want to proceed. And this delta table right now is set for going by ones, right? It's going from 1 to 2 to 3 to 4, like that. Well, what if I wanted it to go by tenths instead, so I could catch these decimals? Then I want to put in a 0.1, so it's going to go by tenths. And to save some time here, I'm going to tell it to start at negative 1.4. Because these are going, you know, this is where it starts. Table start at this. Then I'm going to go back into my table, and it's going to jump right to negative 1.4, and there's my 0. So that one works. And then instead of scrolling to 1.2, I mean, look at how many of these things I've got here. I mean, I could, I suppose. It's not that bad. You know, I could do that all the way up to 1.2, but I could also go into my table set and just put in 1.2, second function table. At 1.2, my y-coordinate's 0. So those indeed are my 3 answers. They all work. Also, if I put in this right here, here, and here, it would produce a 0, and same for the other 2. All right? Now, if this 7/5, I don't know what I had. I don't know if I had 7/6. I can't remember what I had. I did a preview on this, and it didn't work. Oh, shoot, I wish I... Was it 7/6? Does that one go on forever? Yeah, it's this one. See how that doesn't stop? It's irrational. It just goes on and on and on. I can't find that because I can't tell table set to go on forever. So I can never actually get to this number through that. So if it chops off really nice and neat and it's a rational, you know, it's a rational fraction and it works, some of these aren't going to work real well and the numbers are going to keep going, so you can't check this, but you can check these. So you do have to know how to do factoring by hand. And you do know how to check them by hand by throwing in your numbers in here. And you do know how to have to know how to check them with a calculator. I think all 3 methods are real valid. And then number 12 is the same, except it's just, you know, different numbers. All right. Well, why don't we go back to this one and just enter these in here? It doesn't matter on the order, just so that we're clear about how to enter these in. Okay, good job. So there's my 3 solutions. Okay, so that's it for chapter 6. I'm combining chapter 7 in this test because they go really well together. Chapter 7 is all about our rational expressions, and we need all of our factoring to figure them out. So then they go nicely, they're paired nicely. We're going to see why we've done all this factoring for the last, you know, I don't know how many sections, because it's very useful. All right, so I will see you for chapter 7. See you later.